Thanks, folks. Hope you had a chance to get something to drink, maybe a snack at the break here. I'm going to get started. I'm Charles, as you mentioned, from Red Hat. I work on JRuby, JVM language stuff, and I'm going to talk a little bit about some of the cool things we can do with the MethodHandles API. All right, so here's what we're going to cover today. First of all, what are method handles? I'll describe what we're actually talking about here. Why do we need to have these? Why do we need to have the MethodHandle API? What is it doing to serve us? What's coming in Java 9? There's a bunch of additional enhancements, a few new features. I'll talk a little bit about an API I work on called InvokeBinder, which is meant to wrap the MethodHandle API, make it a little easier to use. And then we'll see what other crazy things we might be able to do with them along the way. All right, so what are these method handles things? Well, let's take a little look back at history. Around 2006, JRuby started to become an interesting project, largely because Ruby on Rails was going crazy. Lots of folks were moving over to the Ruby world to start doing web development, and we managed to actually get JRuby to run Rails on the JVM. First time anyone other than the main Ruby implementation had done that. That sparked a lot of interest at Sun Microsystems, and maybe we can make this language be a polyglot VM. Maybe we can bring more than just Java to the platform and support them well. Also around this time, there was a JSR called the Invoke Dynamic JSR, JSR in 292, but it had kind of stalled. Nobody really was sure how to implement it or what the best way to represent it on the JVM was, so it was kind of time for a reboot. Now that the language was starting to be really interesting, we've got something like Ruby on Rails running on the JVM, we wanted to bring better language support to the JVM. So what is it that we needed? And by we, I mean specifically dynamic languages on the JVM, Groovy, JRuby, and so on. Well, we obviously needed to be able to call methods dynamically. We couldn't bind it to a specific signature, specific method like we would in Java code. We had to be able to go look those up in very different sorts of class structures. For example, in Ruby, all classes basically start out empty, and you just fill it up like a hash of key-value pairs, where the key is the name of the method, and the function that represents that method is the actual value. So very different than a Java class structure. We also need to be able to do things like dynamically allocating fields. In Ruby, you don't say what fields your object has ahead of time. As they're assigned, room is made for them in the object. And so that needs to be done dynamically at runtime. And actually, constants in Ruby are sort of lazy constants. They only are accessed, but they're only defined once some code runs behind the scenes. And then we want to bind them very tightly to that value so that we can optimize around it. We also needed it to be fast. So all of these things we were able to do before Invoke Dynamic, using reflection to look up methods and so on, but none of those really optimized well. The JIT couldn't do much with them. We needed a better way of telling the JVM exactly how we wanted these languages to work. So we returned to JSR 292, and a bunch of folks at Sun and folks from various language projects got together, and we got the Invoke Dynamic JSR going again. So there were two parts to this JSR. Part one was a new bytecode added to the JVM for the first time. This essentially allowed you a way to reprogram the JVM, to give it a new way of doing invocation based on your own language. Part two is the MethodHandle API. And the MethodHandle API is what you plug into Invoke Dynamic. Method handles show you how to call a method, how to look up a method, and pass that on to the JVM so that it can inline all of that logic, optimize it, and run it just as fast as if it was regular Java code. So the MethodHandle API is what we're really going to cover today. I've done other talks here in the past on Invoke Dynamic, and you feel free to go check those out. Not a lot has changed as far as how Invoke Dynamic works. But for the MethodHandle API, we'll walk through it here. So the first thing that you'll run into is the MethodHandles.lookup object. This is essentially your Java-lang class that lets you go get methods, go get fields, and get access to them like that. A method type is basically just a representation of a method's return value and the argument types that it would take. So whereas in reflection, you would just pass a list of classes to get method, for example, in this case, you create a method type, and you pass that into the lookup, and it will go find the method for you. And then you can pull out of the lookup object method pointers, field pointers, and array pointers. So we now essentially have something like reflection, a little callable object that represents calling a method or reading and writing fields and array elements. And so then, once you've got those endpoints, the things that you want it to actually do within the JVM, you can wrap it with all sorts of adaptations. You can do branching logic. You can reorder arguments. You can filter one or more arguments and replace them with a new value. And so all of these things together, the direct handles, which are actually doing a call or a write somewhere in memory, plus these adaptations around it, form what we call a method handle tree. Now, I mentioned that it's very similar to reflection. The use cases for parts of method handles are actually very similar. So reflectively looking at methods, reflectively pulling fields out of objects, inspecting and working with classes that you've never seen, stuff you can't write just a piece of Java code for. You want to take in user-defined classes and work with them. And then, of course, some metaprogramming stuff, looking at a class, divining its structure from these APIs, and then generating more code based on that. But method handles do all of this with far less overhead, or kind of optional amounts of overhead, and much better JIT characteristics. The JVM actually can see all the way through method handles and optimize it in ways that reflection just never will. In Java 9 now, it's also starting to replace some of the unsafe operations that we've wanted to get rid of for years. And I'll talk about that a little bit later. All right, so now we'll walk through some basics of using method handles first. I mentioned the method handles lookup object. There's two different ways to get a lookup. The first way, with method handles.justLookup, the word lookup, provides a special type of lookup that can see everything you'd be able to see at that point in the code. So if it's in your class, it can see your class's private fields, private methods, and so on. That's good for you to use if you're using it internally. If you want to expose some internal state to someone outside, you can also give that lookup away. But usually you'd keep this within a particular class so that you can call private methods and access private fields within it. The other one is the public lookup. The public lookup is what you'd expect. This is one that you'll usually be using if you're playing with the API. It only can see things that would be public from anywhere in the Java ecosystem. So public fields, public methods, and so on. So once we have our lookup object, we can go grab some method references here. Here we have 3 different method types and 3 different ways of looking up methods. The first method is the getProperty call on the system class. That's find static to get it, just a static method. The second one, the add method on a list. And we've got the signature for the list there, taking an object and returning int. And we find virtual because it's a method on a particular instance. We also have find constructor. Here we have the constructor for a hash map. And there is a third one called find special, which is used for calling things like overridden methods or private methods and so on, but not important for our concerns, and most folks won't end up needing to use it. All right, accessing a field, very similar call here. We're finding the static getter to get the system out field. As you'd expect, there is find getter and setter for instance fields. So once we have these, we've got our methods, we've got our system out, now we can actually start doing more interesting things with them. I mentioned some of the adaptations that you can do around handles. For example, in this case, we're taking the getProperty method, and we're going to always use java.home as the value that we pass. This now gives us a new handle that knows how to call getProperty and always passes in java.home. And we can continue to build up more complex logic. I'll show some more examples of that later. Once we've built our tree of handles and we've got all of our logic bound into it, we want to call it. Now, there's a couple different ways that you can call methods. The regular invoke and reflection, for example, does a whole lot of extra work for you. It does type checks, it does type value conversions from int to long, and so on. It does boxing and unboxing of values, so var args lists, integer, capital I, and so on. And now a lot of times you don't need that overhead. You know exactly what method you're calling it with the correct types, but reflection isn't particularly smart about this. It's still going to do these checks every time. It's still going to check if there's any type conversions needed, and that's part of the reason why it doesn't optimize as well. Method handles give you 3 different ways to invoke. First of all, invoke with arguments, which is essentially what reflection does. This is the way that you're not sure if these are the right arguments, you're not sure if everything's typed right. It'll do those conversions and do those type checks for you. Invoke removes some of those type conversions and some of those features, reduces a little bit of overhead. And then invoke exact is when you have precisely the right types of values and the number of arguments for calling a target method. It does no extra work for you, but it's the fastest path to doing that call. Now, it's really helpful to kind of look at this through the eyes of a Java programmer and see how a piece of Java code could be converted into a tree of method handles. So we have a simple, hello world version 2, where we're accepting a name in from the command line, concatenating it with hello, and then printing it out again. And we'll walk through this and see what the equivalent method handles would be to do these different things. So first of all, we've got our system out. We saw this earlier, find static getter, the out field on the system class, which is a print stream. Here we have an array access. So we do an array element getter. The array element getter gives us a method handle that takes the array and an index, and then it will always return the result. Down here, we've got the print line call. This is a virtual invocation on print stream to print line, and we're just calling the one that takes a string. And there's actually one more piece of logic in here. We can actually take this concatenation and turn this into a method handle as well. So this would just be find virtual of the concat method on string class. And then here we're actually binding it to hello. So it's always going to call it against the hello string, concatenate the name, and then give you the result. Now, we've got these different handles that do the different pieces of this Java code, but obviously they're not all working together. We'd have to call each of them individually and then maybe get a result out of the end. But we want to be able to combine them in more elaborate ways. So many handle adapters that you'll see in the API can wrap one or more handles. Wrap two or more handles and provide more complex logic. We call these method handle combinators. These combinators allow you to build arbitrarily complex trees of method handles that will do all sorts of logic. Everything that you could represent in a piece of Java code can then basically be turned into method handles, passed to the JVM, and compiled down as a little function object. And the JIT still sees through all of this. It takes that code and generates largely the same assembly, the same native code that you would see if you wrote it in Java by hand. So let's take a look at a couple of simple examples here. The first one is an if-then-else. So we've got a branching logic that we want to represent in our method handle tree. In this case, we're just doing a little contrived database cache here. We check to see if the cached, the requested key is in this hash table. If it is, we'll return the result. If not, we go out to the database, insert this back into the cache, and then from then on, we'll return the cached result. So in the MethodHandles API, you do this with what's called guard with test. It's essentially an if-then-else. Could have been named if-then-else, but this is where to look for it. So I've got our guard with test that takes three different method handles: a condition handle, which will return a Boolean result, and then a then body and an else body. Our condition in this case is just the contains key method on the map class, takes an object and returns a Boolean value. And then we're always going to bind it to our cache object. So now we have a predicate, a condition for our while loop, or a condition for our if that will always use the same cache object, call the contains key method, and return a Boolean for you. We have our then body, so we've found the key. All we need to do is pass that object back, pass that key in again, get it out of the hash, and then return it. And again, we bind this directly to that cache, to that little hash map that we have. And then there's the else branch, where in this case it calls a cache from DB method that will take the hash, go get the database result, and insert it in there. And we bind that to the cache as well. Now, with these three items, these three method handles, we stick them into the guard with test. We get a single handle out that will check for the cache result, return it if it's available, or go get it and cache it. That's pretty cool. And it all optimizes down. We didn't have to generate any code for this. We've got our little function object. Another example is the try-catch combinator in the MethodHandles API. This is just catch exception. And there's a typo here. It's catch exception, and it takes an exception you expect might be raised, like a catch block, the body that you want to protect, and the exception handler that you would pass to. So here, in this case, we want to wrap a little logic around our database access. In case there's some error calling into the database, some error looking up this key, we're going to wrap it in the cache default method. So in this case, if any exception is raised, we will fall into the cache default. It will put some error information into our cache, and then proceed to return that value to us. Now, obviously, there's a lot more adaptations than this. As I say, pretty much anything that you can represent in Java code has a method handle combinator in the MethodHandle API. We can insert arguments or drop arguments, like we inserted the hello string to always call concat against hello. We can permute the arguments. So if we're trying to adapt two APIs, we can reorder arguments in any way we want. We can filter arguments. And this is kind of where you can do your type conversions. So if it turns out that you have an int and you want a long, you can do the particular operations to cast it up. You can also do something that's called folding, conceptually a little more complicated, but you provide a handle, it passes all of the arguments into it. Whatever that result is, it adds it as the first argument. So you can progressively reprocess all the arguments and produce a new value for your method handle stream, for your method handle chain. So let's put this all together. We've got our endpoints, we've got our methods and our field accesses, and we've got our various combinators. Let's try to actually turn that Java code into a method handle tree. So here's what we need to do. We need to load the string from the array. We need to concatenate that string with hello. On the other side, we need to get system.out. And then we need to pull all of those together and call printline to print out the result. So start up at the top. We get our static getter for the system out. We get our array element out of the arguments array. We're going to insert 0 as the first argument here. So it always accesses the 0 element of our array. We're going to grab our concatenate method, and we're going to bind that to hello. We're going to get our printline method. And then we're going to use that fold operation that I mentioned before to reinsert this back into the arguments so that we have the print stream as the first element in our argument list. So we're going to drop the string. We don't care about the string for the purpose of going and getting that out. We just want to grab that field. So we fold it back in. The print stream gets stuck into the argument list. Then we're going to filter this by taking the result of that string, passing it to concatenate, and then sending that on to printline. So the chain goes right down the same way as this last diagram. Filter the arguments again. We've got our name. We have finally at the end a single method handle that will do all of the operations we needed in our Java code. And this will all optimize down and turn into that same native code. Okay. And then we can invoke it at the bottom. So what about Java 9? I mentioned that there are some new things that we've got, essentially missing features. Missing features that when we first started talking about the MethodHandle API, we didn't think these things would be needed, or they just didn't come to mind. One big one that I ran into a lot working on JRuby was there's no try finally. There's a catch exception, with which you can build a try finally, but it's rather complicated, and as I'll show in a moment. There was no way to do a loop. So if you wanted to iterate over several elements, you just kept deepening the stack. And of course, that would eventually blow the stack out. We wanted a proper looping construct within the MethodHandle API. We needed a way to do volatile accesses and atomic accesses. The get and set operations that the MethodHandles API provided was insufficient to be able to replace these volatile operations. And as I said, we want to try and represent everything we can do in Java code using method handles. So these needed to be added. And then oddly enough, there was no way in the MethodHandle API to just tell it to create an array for you. You would always have to pass it, would always have to call out to some utility method that simply knew it up an array and then gave it back to the method handles. Now there's actually a handle operation in the MethodHandle API to construct a particular type of array of a certain size. All right, so we'll take a look at a couple of these new Java 9 features. So try finally is tricky. Some folks know this, not a lot, but when you compile a try finally in Java-C, what it actually does is take that finally logic and stick it on every exit path from that block. So in the simple case, it'll be on the normal return path, right before it returns the value, and it'll be on the exception path, right before it rethrows the exception. And we have to basically reproduce that in the same method handle tree, which makes it very complicated to build a try finally in Java 8. You can imagine we've got our body, we've got to wrap it with the finally, we have to do the return, we've got to wrap that whole thing with a finally for the exception side. It gets very complicated. And the result is that something that looks as simple as this, just wrapping a method handle invocation with try finally logic, ends up turning into this code. And this is actually greatly simplified because it's using that InvokeBinder API I mentioned earlier. It's probably 2 or 3 more pages of MethodHandles API calls to represent a try finally in Java 8. And this is obviously not what we want. This is forcing the JVM to do a lot of work to reinterpret and optimize these handles. We want something simple. And finally in Java 9, we can just say try finally. The JVM understands what we're talking about, and we don't have to build up such a complex graph of method handles. I mentioned that we also have loops of various types. So the simple ones, like a while loop or a do while loop, are available with an initialize that sets up whatever state you're using for the loop, the condition that should be checked on each iteration, and the body that should be executed for each loop. We can also do a counted loop and just say, execute this handle a certain number of times, execute this body a certain number of times. We've got our count, we have the initialization, and we have the body that we want it to call. Similarly, there is an iterated loop. So if we have something that returns an iterator, we can pass the iterator in, do whatever initialization we need for the loop, and it'll iterate over all items within our method handle tree. And that's all pretty cool. These are all basically special cased versions of the general loop call on the MethodHandles API that allows you a great deal of customization. The Java docs for it are like 5 pages long. Usually you're going to just use one of the specialized versions if you're going to use the MethodHandle API. All right, VarHandles, another cool item that came in Java 9. So I mentioned that there was no good way to do volatile accesses or atomic accesses of fields in the MethodHandles API. VarHandles solves all of that. It provides different ways to do volatile operations. You can do compares and swaps without going all the way to unsafe or indirecting through an atomic reference object. It also has a couple cool new features. If you have a byte array that you know actually contains all long values, for example, something that you've read from a data stream or read from the system, now you can treat that byte array as if it actually was just a list of ints or just a list of longs without having to pull byte after byte after byte and make those values yourself, praying for the right endianness and so on. And of course, this is part of the MethodHandles API, so these all convert to method handles. You can mix them right back into your method handle tree, and everything optimizes like we expect. We'll walk through a quick example here. So acquiring a var handle. This is again on the lookup object that we had from MethodHandles API. So here we want a static var handle for the system out class. We can also do a var handle on a particular object, just like the find getter or the find setter. We can get our byte array or byte buffer views, which will pull elements off at a wider stride, a 32-bit stride or 64-bit stride, so you can actually get the data out in the structure that you want it. Oh, and actually, the cool one here, so there is an array element var handle. I showed you that we had ways to do writes, sets and gets into an array. Now we can actually do volatile sets and gets into an array. Atomic operations like compare and swap on an individual array element. Really cool stuff that was almost impossible to do unless you dug into the unsafe API or had it wrap it around, with an atomic array reference. Okay. So here's how we can do the atomic and volatile accesses. And like I say, this works with an array, this works with fields. Compare and set is in there, volatile write, volatile read, weak volatile, all of the stuff that we expect to have from the Java memory model are available as operations on a var handle against either a field or an array element. Here is using the byte view var handle to treat a byte array as if it's actually just made up of longs. And actually, that should be divided by 8 there. So we pull our byte array off of some I/O stream, and then we can actually read it as longs rather than reading it as individual bytes. 8 times less work of pulling bytes out of this and recombining them into longs. The VarHandle API does all that for us. And as I mentioned, you can mix the var handle into a method handle tree. Just varhandle.toMethodHandle and it mixes right back in. You can use it with all the other methods in your handle tree. Okay. So I mentioned InvokeBinder a couple times. Let's take a look at how InvokeBinder makes this all a little bit easier. Some of these things are a little arcane, like folding arguments and whatnot, and InvokeBinder simplifies a lot of that. So now when you look at this code, it doesn't look particularly elegant. There is a lot of noise here. There's a lot of long method names, a lot of duplication, string, 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 all over the place. I think we've established that we're passing a string in. Why do we have to keep doing it? Well, these are all individual calls. There's no context that goes along with it, and so it ends up noising up our code a lot. Part of the problem here is that we kind of compose these method handles in reverse. We need to grab the target method, and then we need to wrap some logic around that. We need to wrap an if statement around that. We need to wrap some try-catch around that. And it gets very awkward for us. It's kind of like trying to write with the incorrect hand, with the hand you're not used to. We write our code going forward, and the MethodHandles API composes it backwards. So that's something that InvokeBinder helps with a lot. It also reduces a lot of the repetitiveness. You start at the top, and you say, I want these arguments and these return value. From then on, the InvokeBinder builder API knows the types you're talking about. You don't have to keep passing them in and constantly telling it that you're using a string argument. So if we take the InvokeBinder API and we use that to do this logic, to create our little hello world method handle tree, we're able to turn this code into this code. Much simpler. Now we can actually read through this and understand what's going on. All right, so we'll go through some basic use here of the InvokeBinder API. So starting off, you say binder.from with some method type or with a return value and arguments. Now it knows what you're expecting to pass into the top of your method handle tree. You can do all of the operations simplified down to just simple words, drop arguments, insert arguments, permute arguments, and so on. You can do your folds and your filters and pass in a lambda to do the additional logic for that folded operation or for the filter that you want to do on a particular argument. And then it provides the final step where you've got all these different invokes. So you can basically commit everything that you've written into this little builder API. It will recompose all of that into method handles and give you the result. And there's also utilities for some larger operations. For example, I mentioned Java 8 didn't have a try finally, and no one wants to have to rewrite all of that logic I showed. So in InvokeBinder, there was a try finally operation that did that for you. On Java 9 now, it will just call the appropriate method on the MethodHandle API. So let's walk through what's going on here. So we start out at the top. We know we're going to pass in a string array, our arguments, to the main method, and we don't care about any return value. It's just void. We are going to filter that string array with an array get operation against the 0th element. Now we have a string as our argument. In the next one, we have our concatenate call. So we're going to prepend hello, call the concatenate method, and now we have our new string. We can get our print stream. So in this case, we just drop the arguments, go get the system out field, and reinsert that back into our call chain. Now we have our print stream as the first argument, our hello name as the second argument. We do our invoke virtual, and it will call we have our print line. Now we've got our handle all constructed together in significantly less code than if we wrote it manually. Down at the bottom, we can do our invoke, and we've got it all working. Okay. So now I mentioned that we can do something a little bit, we might be able to do something a little bit crazy with this. So with the addition of loops in Java 9, the MethodHandle API is really pretty much Turing Complete. It was kind of Turing Complete before if you had an infinitely long stack. Now we can do loops and actually generate essentially any set of expressions, any piece of Java code as a chain of method handles. So we can modify state in memory. We can call methods. We can have conditional logic. We can execute loops. We can turn pretty much any language on the JVM into a chain of method handles. So why not try this? I thought maybe I'd try to do this for Ruby. So what we're going to do, we're going to take the JRuby AST of parsed Ruby code, and we're going to visit our way through that abstract syntax tree. For each syntactic element, we will replace it with what the method handle operation would be at that point. and I'll show you a few examples. We will, in this case, just store some local variable state in an object array. So we start out with an object array at the top. All of our local variable gets and sets will go in there, and it just stays in the method handle tree as if it was just regular variables. And the only things that I have implemented at this point when playing around with this, I've got some simple numeric operations, some conditionals, and some loops. But we'll see how we can turn some Ruby code into method handles here. This is the top level of the compiler. Again, just a quick experiment. The important parts here was that we're going to parse that Ruby code that's been passed in on the command line and then pass it into our handle compiler to be visited and turned into method handles. The visitor pattern, everybody should be pretty familiar with this. For each node that we encounter, we're going to tell that node to call us back. That node will call the appropriate method, and then we'll build the handles for it. Two examples of constant values, constant keywords in the Ruby language. So if we have a false in our Ruby code, we're going to insert the Boolean false object here. If we have a true, we insert a Boolean true. If we have a particular numeric value, in Ruby, a fixed num is essentially a 64-bit long. So we're just going to insert a long object here into our chain of method handles. I mentioned local variable node, or mentioned local variables. We pass in our object array that has all of the local variable state for our little call, and then we get whatever the element is. Find the index, pull that element out. The assignment is a little bit more complicated here because the array set operation in the MethodHandle API returns no value. So we have to sort of use the folding operation to insert it into the array off to the side and also return that value. We can do conditionals. So we have an if-then-else in Ruby. We take our three pieces of the AST and pass them down to the rest of the visitor. Now we have our conditional, we have our then body and our else body. We're going to use filter return value here to take whatever the result of that condition was and Booleanify it. So in this case, as in Ruby, anything that's null or the false object will be considered false. Everything else would be true. And then we pass that to guard with test. Now we have a representation of a Ruby if-then-else in method handles. And now that we have loops, we can also do while loops in the Ruby language. We compile our predicate for the loop. We compile our body for the loop. We check whether we're doing a while or a do while. And then we compose these together using either the while loop call or the do while loop. And the last little piece that I can show you here, at the root of our script, is where we set everything up. So we compile the body of the script. That gives us the handle that represents the entire logic of the script that we're compiling. We're going to look at the scope that goes along with this script to see how many local variables it has. We're going to mix back in an array construction operation that creates that array for us. So every time we call this script now, it will create a local variable array, pass it down, and all of our handles will be able to operate against it. So, this is kind of crazy, but does it work? Well, obviously I wouldn't be telling you about it if it didn't work. Here we have an example with a simple loop that just iterates 1,000,000 times, and then I have it set up so that whatever the last value in this script is, that'll print out that value on the console. Here's our AST that was dumped out for it, and of course it ran through and it actually did execute this code. And that's pretty cool. So I wrote a little compiler that turns a piece of Ruby code into a method handle tree. Now, does it work well? Obviously, I've been telling you that this is supposed to optimize, the JVM is supposed to turn it into native code, and it's thrilling and I'm really excited to be able to say, absolutely does. So you can take this expression language, you can take any language that you want, turn it into a method handle tree, and we've made a native compiler for it without generating any bytecode, without loading any classes, just by building up these method handles and letting the JVM optimize it. That's pretty cool. So think about this in terms of query APIs. If you build up queries, you don't have to do all the extra bookkeeping and logic of generating bytecode for those, loading those bytecodes in, making sure that they don't leak or get garbage collected on a timely basis, and so on. You can turn that expression, turn that query into a tree of method handles, and the JVM will optimize it and turn it into native code for you. That's pretty awesome. So really the results on this? It does work. At the moment, the compiled code takes a little while to optimize to native. It functions right away, but we know how the JVM has its warm up and kind of decides to optimize things on its own schedule. So it does take a little while. In my example, the 10,000 iteration limit of the C2 compiler was not quite enough to get it to fire, so I bumped it up to 100,000, then it dumped out the native code just fine. So similar characteristics to when regular Java code will JIT, but maybe a little bit more time to get going. There's also an issue because the MethodHandles API, internally, it lazily kind of optimizes itself. So we're both waiting for the MethodHandle API to say, yes, you've hit this handle tree long enough times, now I'll do my internal optimization, and then the JVM will pick it up sometime after that. So it does take a little bit of time to get it going. So in this particular example, maybe a toy. I'm going to continue on and see if I can get it to run actual Ruby code, see how much of it I can actually represent and whether it turns into a nice compiler. But it is an interesting case. You can see that there'll be a lot of practical cases for being able to programmatically turn an expression into a method handle tree and get this fast callable object out of it. So what about something a little bit less crazy than this? Well, in the last talk, we heard about the Streams API, and everybody that's been doing Java 8 and plus probably just loves them. I do. We just recently moved a JRuby to require Java 8 so that we could start using lambdas and streams. But there are some issues with the Streams API. So most JVMs are not going to be able to inline through map and collect and filter operations. The problem here is that everybody in the world is calling the same map and the same collect and filter. They're passing in different lists. They're passing in different lambdas. And so the JVM has no idea how to optimize those for each individual use case. Generally, all you'll see is that, say, map would inline, and then it will do a call out and doesn't do the optimizations that we expect from the JVM. Now, MethodHandles can do this. MethodHandles can inline. MethodHandles will specialize to the place you call them. They will all fold back in and be inlined right at that location. So why can't we just re-implement streams as handles? And that's the next step that I want to take with this experiment of turning Ruby into a method handle tree. So maybe in the future what we'll be able to do is say, take some stream binder where you've got some list that we want to turn into a set in this process. We're going to process all the elements. We're going to filter a couple things out of it. And then down at the bottom, we'll collect it into a set. And ideally, this should all optimize. This should all inline. And multiple people can use this same function with different types of lists in different locations and get fully optimized code all inlined without any extra calls. That's what I hope we're going for. All right, so wrapping up here, hopefully you can see the MethodHandle API is really powerful. It's one of the most powerful tools that we have on the JVM, and it gives you this potential to essentially represent any expression and get a fast callable object out of it. Obviously, InvokeBinder makes it a little easier to work with. I strongly recommend that you try playing with InvokeBinder if you're going to get into this API. It'll save you a lot of headaches. It also has some error reporting, so that along the way you get a little bit more information about why you had a type mismatch or a problem with the number of arguments, for example. There's obviously a lot of use cases that we have yet to explore. When we originally created this, it was mostly to help other JVM languages, dynamic languages specifically. But it's been used to create the lambdas now. Lambdas use invoke dynamic under the covers. We could do more. We could put it into the Streams API. We could optimize stuff better as a result. So definitely go out there, play with this API, see what kind of ideas you can come up with. I'm sure everybody in here has something they could probably use MethodHandles for. And that's all I have. Thanks very much.
Do we have any questions? Over here.
All right.
Where you could read byte arrays as int longs and so on, would it be possible to read a byte array as an unsigned int? I mean, I read quite data streams coming from other languages like C, and they send unsigned ints.
Right,
but
right.
it would be much easier for me if I could read them as unsigned ints. Right.
Yeah, well, obviously the problem there is that you can read unsigned values out of a byte array, but you still got to put them into something in Java, right? So what you would probably do with this is you would take your VarHandle view of a byte array, and you would just essentially mix in the operation of masking off the bits that you need to get the unsigned value. So you still get the raw bits out of it, but maybe you can at least get rid of the extra masking that you have to do. Until we have an actual unsigned type in the Java language, it's probably about the best that we can do.
Anyone else? Over here.
And of course, you can read a byte array as doubles and floats and other stuff too.
Question about the performance. So you mentioned it all inlines nicely in compiles. Are you aware of any benchmarks that the GMH-like benchmarks that basically where you can evaluate not only MethodHandle performance but also how they enhance as we get new updates?
Right. So benchmarks, I don't know of any benchmark suites or collection of benchmarks out there for MethodHandles API. Certainly nothing that would go to this level of complexity in the chain of handles. That's something that we need. And a little note on performance. Currently, the overhead for doing a call of an arbitrary handle, so if it's not a static final somewhere, is better than reflection, but not by a great deal. So if you're just taking a method handle and doing a simple call, you're probably not going to get a whole lot of gain over reflection. It's really in the combination of all of the handles together into a large expression tree that it all optimizes, and that front-end cost kind of gets blunted. However, if you have method handles that's in a static final somewhere, the JVM will see it's always the same method handle. It doesn't have to have that extra wrapper logic around the top, and that will optimize as if it was just a direct Java call. But we definitely don't have a good suite of performance tests that I know of, and we probably should work on that.
Yeah, over there, of course. If anyone else has a question, put your hands up while he's speaking.
Hey, thanks for the talk. So on one hand, you have the Java people kind of digging into the runtime with stuff like what you presented. And then on the other hand, you have the JVM people with Graal kind of going the other direction, implementing the runtime in Java. So looking ahead, what happens when these two digging crews meet? Like, would you have a unified sort of the metaprogramming framework, or what do you think?
Well, there's a lot that's possible from this. So Graal obviously is a much more complicated version of a compiler written in Java. I would not pretend that what I'm doing with the method handles has any comparison to Graal, but you do have to be a lot more. You have to understand a lot more about compilers to actually work with Graal as an API. It's very complex. There's lots of elements in the IR, lots of different passes that have to be run. This looks a lot easier to me as far as building up a little expression compiler. What I hope we see in the future is that technologies like Graal maybe are used under the cover of method handles to do some of that optimization a little bit more quickly, to get it down to native code without having so many iterations to get there. But yeah, we've kind of got this perfect storm of compiler technologies and expression things coming together on the JVM, and it's up to us to see what we want to do with it.
Anyone else?
Anything else?
I take that as a no. Thank you very much.
All right, thank you.